Okay, we're going to continue on in Chapter 3. In particular, we were up to 3.3.2.1, so I'm going to put the hashtag and that section number up here in the URL bar and take us straight to that section where we're talking about data transfer. And we've talked about sources and destinations as far as messages. And what we're going to do is talk about network addresses. So these are the way that we do that. And in particular, if we're in the local LAN, we're going to use MAC addresses. If we're sending something off the local network, then we're going to use IP address, which they're mentioning in the text over here to the right. We'll talk about layer 3, which is the internet layer, so we'll be talking about internet protocol to go along with that. But primarily what we're interested in right now is the destination and source addresses that we will be sending. And in this case, they're showing a layer 3 address being sent. The PDU for layer 3 is a packet. So they're showing IP packets going from the PC1 on the left to its final destination, the web server on the right. And we'll have a packet that gives the IP address of where the packet originated and the destination address that it's going to. And as we travel through each of these routers, router 1, router 2, and when it makes it to the destination address will be examined to figure out what the router should do with the packet and whether the server should process the packet or not. One thing that I don't think we've mentioned is IP version 4. The IP address in the packet is actually 32 ones and zeros. A byte is 8 bits. That means a 32-bit IP address takes up 4 bytes. So what they do to make it a little easier for us to deal with as humans is it takes each of those bytes and considers it a decimal number and then converts it into what's called decimal dotted notation, like this source IP address, which is 192.168.1.10. So, probably a question on the exam, something you should know is how many bits are in an IP address. And if I say IP and don't specify, then I'm talking IP version 4, and the answer is 32 bits. Now we'll talk about IP version 6 in more detail and why IP version 6 even exists. Short answer is because we were running out of IP addresses. But in IP version 6, IP address is 128 bits. So from a bit standpoint, 4 times as long, but exponentially bigger. So for a 32-bit number, it's 2 to the 32 minus 1 is the largest number you can have, and that's like 4,186,000,000, I believe, some odd IP addresses. Well, if you take that up to 128 bits, it's something like a 6 with like 30 zeros after it or some crazy big number. But we'll talk about IP version 6 in more detail down the road. So that was layer 3. At layer 2, what we have is MAC addresses. MAC stands for Media Access Control. You should probably know that. You should know at layer 2 we're talking about the local network, and that's where MAC addresses are used to communicate with other devices on the same other MAC address. An IP address uniquely identifies a machine within the world. A MAC address is a 48-bit number. Again, probably a question will be asked on the first exam. And it uniquely represents the NIC card, the network interface card, uniquely on the local area network. So if you have source and destination MACs in the Ethernet frames that are sending. So it'll be the MAC address of the source NIC and the MAC address of the destination NIC. Here they're showing encapsulation. We have an IP packet that is encapsulated into an IP frame. Right now all we care about is the headers. So what happens is for this PC to communicate with this router, it sends it to the MAC address associated with this NIC. This router will strip off the layer 2 headers and examine the IP packet to determine what network it needs to go to. In this case, this router decided that the packet needed to go to this router, so it will stick a new layer 2 header with the source address being the MAC address of this interface on the router and the destination being the MAC address of this interface on the router. So we kind of we start at layer 7, we're coming down, we're encapsulating, and then we go to the router and we de-encapsulate one layer, so we can go up to layer 3. We make routing decisions, and then we will re-encapsulate it down into a layer 2 packet. So as it's traveling through routers, it'll keep stripping off the layer 2 headers, examining the IP address to figure out what to do, and then put a new layer 2 a header on that. Let me see what's on 2. So yeah, figures 2 and 3 are just showing you that process. The other thing I want to mention is if you take a 48-bit MAC address and you divide it in half, the first half, the first 24 bits, is referred to as the OUI, the organizationally unique identifier. From that number, you can figure out who manufactured the NIC card. And actually, in an upcoming assignment, I have you look up several OUIs based on MAC addresses that I give you, and then the very last one is usually the MAC address of the PC you're on, so you can see who made it. And I'll go ahead and give you a hint. Sometimes just because the computer says Dell on it, maybe Dell made the NIC card, maybe they didn't, so you shouldn't make that assumption. So this is talking about communicating with devices that are on the same network. To make the MAC addresses easier, they're just using all A's and all B's and all C's for that. So what happens is we use something that we haven't talked about called the subnet mask. And basically what the subnet mask does is it divides those 32 bits that make up the IP address somewhere in the middle. When we start, and the way it was years and years ago, it was always dividing on the decimal. So if you divided at the first decimal point, you had a Class A network. If you divided in the middle, you had a Class B. And if you divided at the third period, you had a Class C network. We now use classless subnetting, but we usually start with the division points being on those periods because it just makes it a little easier to talk about and understand. So in this case, we are dividing at the third period. So the network portion of the address is 192.168.1, and the source host is the host number 110 on that network. We're going to 192.168.1.9. If we use the same subnet mask, we get a network of 168.1. And for both the source and the destination, that network portion is the same. So we would make the statement that these two hosts are on the same network because they have the same network number. I think the curriculum also talks about ARP address. That's Address Resolution Protocol. So what happens is basically a message will be sent out and says who has this IP address, and then a device will answer back and say, I do, here's my MAC address. Now once it has the MAC address, it's able to send the layer 2 frame to that device, so it can either be received by that device or passed on down from router to router to make it to its final destination. In this case, if you look at the source and destination IP addresses, notice that the network numbers are different. So that means that these networks are not on the same network. And if that happens, what you do is you send the packet to something called, sometimes it's called default gateway, default router, gateway of last resort. But basically, if it's on a different network, you send it to your router and basically say, this packet's off my network, deal with it. And it will look at its routing tables and try to get that packet to the next hop. And that process continues until it makes it to the final destination, in this case 172.16.1.99, which is the web server on the right. Now, a lot of times we are going to spend time talking about IP addresses, also talking about Ethernet frames and IP packets and that type of thing. So there is a tool that can aid you as a network engineer called Wireshark. Wireshark is a network sniffer, or official name is a protocol analyzer. And what it does is it reads packets off the network and then stores them and presents them to you, and will actually decode them. Wireshark is a pretty nice thing, just like Packet Tracer is for a simulated environment. So we'll have a number of activities over the course of the semester that uses Wireshark. So Lab 3411 should be appearing in Blackboard shortly. It's entitled Installing Wireshark. It's a fairly straightforward one. One thing I mentioned in the notes of that lab is that the installation instructions are for Windows, but I'm a Mac user myself, and there is a version of Wireshark that works perfectly fine on Mac OS X. So you need to download the appropriate version, install it, and then I ask you to show me a couple of specific screen grabs so that I can make sure that it's installed and working correctly on your machine. Lab 3412 on the next page of the curriculum is called Using Wireshark to View Network Traffic. I am going to assign this. It's 16 pages long, but it's step by step, going through capturing packets, going through looking at packets. I think it talks about saving a capture so that if you need to go back at a later point in time and look at it, or take that packet. A lot of times vendors, when something's not working correctly and you suspect that it's network related, they'll say, hey, can you get a copy of some packets that are traversing the network so that we can look at it and see if we can figure out what's going wrong. This is technically a class activity. I'm not going to sign it, but it just basically summarizes a number of things we've talked about, particularly the OSI model and the TCP/IP model. So you might want to click on the link at the bottom and just read this. It's very short. So that takes us to the Chapter 3 summary. You can read to the content at the right, but it's just basically summarizing some of the highlights of the chapter. With us finishing Chapter 3, you should expect an announcement regarding your Chapter 3 exam. So we'll continue on here shortly in chapter 4.